Remember in the previous section, we saw that exponential functions are one-to-one. And that one-to-oneness of exponential functions guaranteed this that we would have an inverse. So the inverse is going to be the logs. Remember the definition of the exponential function? It said that we had to have y equals a to the x, where a had to be bigger than 0 and a could not be equal to 1, because that would be boring, and x could be anything we wanted it to be. Well, the definition of the logarithmic function has the same conditions on a. The base has to be bigger than 0, a cannot be equal to 1, and then we have this. And this is read, y is the logarithm to the base of a of x. A is a subscript here. A is called the base of the log, and guess what it was called up here? The base of the exponent. So A is the base, and the base of the log is the same as the base of the exponent. How do we get an inverse from a function? Do y'all remember that from your homework? Switch the x and y. Well, look at this right here. Didn't I take this exponential function and I switched the x and y from what it was up here? Well, that's why this condition is here. Remember our IFF, our if and only if? We use this logarithmic notation rather than writing x equals a to the y, thinking that we just made a mistake with our exponential notation. We introduced this notation. Now what I want to point out to you also is the log is equal to the exponent. So a is the base, and a log actually is an exponent in an exponential equation. Whenever we have a logarithmic equation, this part right here, x, is called the argument of the log. The argument, the x, stands alone. Do you like to hang around people that argue? No. So that's why I say this to help you see how these parts fit together. All of this is designed to help you see how the parts on the log relate to the parts on the exponent. So the base of the log is the base of the exponent when we rewrite a log as an exponent. Whatever the log is equal to is the exponent, and the argument of the log stands alone. Now here's what I have a hard time getting people to understand. A log is a mathematical operation, just like addition or subtraction is a mathematical operation. It's just that addition and subtraction we learned in grade school, so we're more comfortable with it. Log we're not as comfortable with. In kindergarten you learned how to count and you thought you were all that in a bag of chips. And then in first grade we taught you how to take those numbers that you counted and combine them using this operation, and you were all that in a bag of chips. But then in second grade we introduce this symbol and you think, ooh, I don't like this operation. I like this operation. And then you kind of got more comfortable with that when you saw the relationship between things. And then in third grade, we introduced you to this operation, and you didn't like it that much either the first time you saw it until you realized, oh, it's just repeated addition. We take it back to what we learned earlier. And then those evil teachers introduced this operation. And you said, oh, I'm never going to learn this. But once you've mastered these, that came second nature. Just took a little more work. And then along about junior high, we introduced exponents to you and roots. This operation means nothing without something underneath it. You're not as comfortable with this operation as you are with this operation because you learned that operation later in life. Well, now I'm giving you a new operation. And this operation right here, you don't want to think of as an operation because it looks like a word to us. Because in kindergarten, we also learned our alphabet. And letters and numbers we learned don't mix. When they do, it makes that a cursed algebra. Well, I'm telling you now, these letters in this particular combination, even though it looks like log, is actually a mathematical operation, just like these are mathematical operations. And just like these operations mean nothing without numbers in them, this operation means nothing without a number in it. You've got to have an argument if you're going to have a log. You've got to have an argument. Log by itself is just like saying square root. You keep waiting, the square root of what? And there's rules associated with how we can change this argument, and we're going to learn those in the next section. Just like there's rules on how we can combine numbers underneath the radical. Okay, there's things that you can do in certain situations. We have rules for how we manipulate the argument on the log, and we're going to learn those. So I just want to make clear what a log is. A log is an exponent when it comes to shove. How we get that exponent then we're going to work on. But a log is an inverse of an exponential equation. Because we can switch x and y to get the inverse, I can take this log notation and rewrite it as an equivalent exponent, always and forever, and I do it using these rules. So let's look at an example problem. Let's change an exponential statement to a logarithmic statement. So here's an exponent, 1.2 raised to the third equals m. So this becomes log base 1.2 of something equals something. What goes right here? The argument stands alone. That's why I wrote these things down up here. The base of the log is the base of the exponent. The log is equal to the exponent. So what this log is equal to is 3, the exponent. And then the argument stands alone. I'm going to repeat this enough, it's going to get stuck in your head. The next one, we have e to the b equals 9. I'm going to rewrite this as a log. This becomes log base what? Of equals, the base of the log is the same as the base of the exponent. The argument of the log stands alone as an exponent, and the log is equal to the exponent. Let's rewrite this where the log is on the right now. What's going to go over here? Whatever the log is equal to is the exponent. So 4 equals log base a of 24. Do you see how to rewrite an exponent as a log? Can you do the opposite and rewrite a log as an exponent? Sure. You should got to be able to go both ways, back and forth, just like our division and multiplication kind of go back and forth. What's the base going to be? 2 the equals. What's the base going to be? E to the equals, and 3 to the equals. Sometimes it takes a while to get this, and sometimes it helps when I introduce you to Ben and Benny. Here's Ben. Hi, Ben. Here's Benny. B-N-E. Ben is easy to remember. B to the E equals N. And then for the log, we have Benny. B-N-E. Okay, it's corny. Logs are cool. You can find an exact value of a log. And here's how we're going to do it. If you don't know what this is, and because you haven't worked with this operation as long as you've worked with these operations, these are going to take a little bit of time and figuring to get comfortable with. So what we're going to do is we're going to introduce a y to this problem. We're going to say y equals log base 3 of 81. And if I can solve for y, I'm there. Rewrite that log equation as an exponent. What will the equivalent exponent be? 3 to the y equals, well, now I know how to use the one-to-one property of exponents, and 3 to the y is the same thing as 3 to the fourth. And so that means that this expression is going to be equal to what? It's 4. Log base 3 of 81 is 4. Now let's figure this one out. So we're going to introduce a y, log base 2 of 1/8. Let's rewrite this now as an equivalent exponent. What's my base going to be? 2 to the equals 1/8. Well, 1/8 I can rewrite as 2 to what power? -3. So guess what y is equal to? That means that this log is equal to -3. We're just manipulating symbols. We're just pushing them around is all we're doing. The first thing I did was I introduced a y, and that gave me an equation. Then I rewrite a log as an exponent. And then I rewrite the exponent with a base of 2. So because it's a fraction, I knew I could use a negative exponent, and 2 to the third is 8. So that's why that was 2 to the -3. 1 over 8 is the same thing as 1 over 2 cubed. But I didn't want the 1 over. I wanted my base to be 2, which means that I had to make the exponent unhappy by moving it. Remember, another deal with the inverse functions is we end up swapping domains and ranges. So the domain of the exponential function becomes the range of the log and vice versa. So the domain of the log is the same as the range of the exponent, and that's 0 to infinity. That means we cannot take the log of a negative number or 0. The range of the log is the domain of the exponent, which is going to be negative infinity to infinity. So that gives us this. We can use that restriction on the domains to find the domain for each of these logarithmic functions. What do we know about the domain of a log? Has to be non-negative. So on part A here, to find the domain, all I do is I take the argument and I set it greater than 0 to find out what x can be. That argument has to be non-negative. How do I get the x by itself? Added to both sides. What you do to one side, you have to do to the other. No flipping of the inequalities or anything. So that means the domain of this function will go from 2 to infinity. That's the domain for part A. X has to be greater than 2. Part B. Now I have this function. It's a rational function, and I have to set the argument greater than 0 because the argument cannot be equal to 0 or negative. Well, guys, this is a rational inequality like what we solved last time on our test. So in order to solve this inequality, we're going to find our critical points, divide the number line into intervals, and see which ones make this inequality true. So this first interval goes from negative infinity to negative 3 to 1, and 1 to infinity. Negative 3 is the critical point from the numerator, and positive 1 is the critical point from the denominator. Should there be brackets? We have a strict inequality. See, on a logarithmic function, we cannot be equal to 0. The domain cannot include 0, so it's a strict inequality. So let's test x equals negative 4. We end up getting negative 4 plus 3 is negative. Negative 4 minus 1 is negative, and a negative over a negative is positive. So we're okay there. Go to the next interval. What do you want to test? I like 0. That gives us a negative because a positive over a negative is negative. And then go to the next interval, and that's a positive over a positive. So our domain here is going to be the interval that goes from negative infinity to negative 3 union 1 to infinity is the domain of capital F of x. And then what about C? Absolute values are always positive. We just got to worry about where this thing is equal to 0. So here the domain would be x is not equal to 1. If you want to write it like this, you can. The question here strictly asked about the domain. Make sure you understand what the question's asking before you take off working. We know lots of stuff right now about logs. Now, the other thing we learned about inverse functions is that the graphs of inverse functions are symmetric about the line y equals x. Look at this blue function right here. This is our exponential function where the base is between 0 and 1. Remember, it's a decreasing function. The domain is all real numbers. The range goes from 0 to infinity. If we were to reflect that shape across the line y equals x, we end up with the graph of the logarithmic function. The domain goes from 0 to infinity, so we have a vertical asymptote. Instead of having a y-intercept at 0, 1, we have an x-intercept at 1, 0. Remember, you switch x and y to get from the inverse to the function and vice versa. So we switched x and y. So here's an exponential function where it's increasing. That means the base is bigger than 1. Here's an equivalent logarithmic function where the base is bigger than 1. We have 4 new parent functions now that we've added to our arsenal of parent functions. But they're all variations on a theme. If you understand properties of inverses and properties of just one, you can figure out the other. You know the exponents, and you know that logs are inverses of exponents. You can figure out all of these properties of logarithmic functions. So the domain for a log is going to be the set of all positive real numbers. The range is all real numbers. We have an x-intercept at 1, 0. There's no y-intercept. The y-axis is now a vertical asymptote. A logarithmic function is still going to be decreasing if the base is a proper fraction, and it's going to be increasing if the base is bigger than 1. Increasing, increasing. Decreasing, decreasing. And the graph contains the points 1, 0, a, 1, and 1 over a, negative 1. These are the similar points that we had on the exponential functions. I didn't stress these that much. This is the one that I really want you to know. The other two, I mean, to me, they just make sense intuitively. If they don't make sense to you, ask and you shall receive an answer. If you have y equals a to the x, that's an exponential function, and x is 1, don't you get y equals a? Well, if you switch x and y, you get this point. If it's a negative 1, you get the reciprocal of that. We have two special types of logs. We have a natural log and a common log. I'm going to organize this information a little bit differently. We have the names of these functions. The names of the functions are common log and natural log. I want to write down what it means. Common log means y equals log base e of x. A natural log means y equals log base 10 of x. But what we write, and what we write here though, is ln x, and what we write here is just a log without a base. These are our special logs, and these happen to be the log buttons that you have available on your calculator. Here's the common log button, and right below it is the natural log button. If you look right above in blue, in my case it may be yellow on your calculator, the inverse functions are always right above the functions. The inverse of a square is a square root. The inverse of a log is 10 to the x. The inverse of a natural log is e to the x. So if you ever see this written, y equals ln x, I want you to be thinking log base e of x. If you ever see a log without a base, you know it's a log base 10, because that's our common base numbering system. So we can solve logarithmic equations then using properties of logs and common logs and natural logs. So let's look at this problem right here. I want to solve this logarithmic equation. If you can't get x by itself with it written as a log, we're going to rewrite this log as an exponent. How would I rewrite this log right here as an exponent in order to 2 to the third equals, if you can't figure out what x is with it written as a log, try rewriting it as an exponent. 2 to the third is, so we have 8 equals 2x plus 1. Now what? Subtract 1 from both sides. So 7 equals 2x, so x is going to be equal to 7 halves. This is a log base 2. It's neither a natural log nor a common log. A natural log is a log base e. A common log is a log base 10. This happens to be a log base 2. We don't have a button for it on the calculator. Alright, let's look at this problem. I don't know what it is written as a log, so I'm going to rewrite it as an exponent. Rewrite this log as an exponent for me. And in order to get that power off of there, what do I need to do? Do you have a cube root button on your calculator? You do, but I don't. What would it look like? I'm glad you asked. When you raise a power to a power, don't you multiply the exponents? So this becomes x to the first, which is what we're looking for, equals 343 to the 1/3 power. On your calculator then, you can type in 343 raised to the, open parentheses, 1 divided by 3. So we get x is equal to 7. Remember, we can use rational exponents as opposed to radicals. It's easier to change that. Thank you so much. I'm glad you mentioned that. Let's use logs to solve this one now. The first thing we want to do is we want to isolate the term with the variable in it. So we're going to divide both sides by 2. And that's going to give us e to the 3x equals 3. Now rewrite it as a log. So this becomes log base e of 3 equals 3x. How do we get the x by itself? Divide by 3. So what we're going to get now then is x equals the natural log of 3 divided by 3 on your calculator. We're going to hit ln 3, close the parentheses, and divide by 3. And so this is the exact value. It's approximately 0.3662. This is a decimal approximation. Only give that if I ask for it. This is the exact answer. That's the one I'm going for. Now, we can use logs in the real world to model situations, and one of the ways we use it is by using a decay type thing. Alcohol and drugs leave your body through an exponential process. It says blood alcohol concentration, BAC, is a measure of the amount of alcohol in a person's bloodstream. A BAC of 0.04 means that a person has 4 parts of alcohol per 10,000 parts of blood in the body. Relative risk is defined as the likelihood of one event occurring divided by the likelihood of a second event occurring. For example, if an individual with a blood alcohol concentration of 0.02 is 1.4 times as likely to have a car accident as an individual that has not been drinking, the relative risk of an accident with a BAC of 0.02 is 1.4. Recent medical research suggests that the relative risk of having an accident while driving a car can be modeled by this equation right here, where X is the percent concentration of alcohol in the bloodstream and K is a constant. Our first step here is going to be to find the constant K in the equation. So research indicates that the relative risk of a person having an accident with a blood alcohol concentration of 0.02% is 1.4. Starting with this equation, we have R equals E to the K X. X is the percent concentration, so we get R 1.4 equals E to the K times 0.02. Can we solve this equation for K? Sure we can. Another way of writing this is 1.4 equals E raised to the 0.02 times K. Raised to the K, because when you multiply the exponents, you're using that property that says you can raise a power to a power. Actually, there's no need to do this. We can rewrite it as a log. So this is going to be log base E of what? Equals K times 0.02. I'll say 0.02K. What is log base E? ln of 1.4 equals 0.02K. So K is going to be equal to, so K is approximately equal to 16.8236. I'm going to put in the percent concentration as a whole number. I've just taken this and multiplied everything by 100 is essentially what I've done. It depends on how you set it up. X is going to be the percent concentration written as a percent. If I wrote it as a decimal, this would be 0.168. Using this value of K, what is the relative risk of a concentration of 0.17? See, so now we're going to rewrite our function R equals E to the 16.836x. And we're going to plug in not 0.0017, but 0.17 for x, because that's the constant that I'm using. So I'm going to look at R of 0.17 times, oops, not okay, 0.17. And what do you get then for your risk? Second ln, E raised to the 16.8236 times 0.17 is 17.46. So you're 17 times or 17.5 times more likely to be involved in an accident if your blood alcohol is 0.17. The next question is, using the same value of K, what blood alcohol concentration corresponds to a relative risk of 100%? So now we're going to plug in 100 for R, and we're going to get the blood alcohol concentration equals E to the 16.8236 X. How do I get the X by itself? Log base E of 100 equals 16.8236x. Solving this equation for x, divide both sides by 16.8236. Somebody get me this number right fast. This is a log base E, or a natural log. So x is the natural log of 100 divided by 16.8236. So, or 100 times the risk if your blood alcohol is 0.27. If the law asserts that anyone with a relative risk of 5 or more should not have driving privileges, at what concentration of alcohol? How would we determine this? Plug in a 5 for what? R, and solve for x. So you guys can do that. We'll stop this recording.